Hello, everyone. Welcome to this session um, where we present reputation-based weighted voting live from DEF CON. So I'm here at the DEF CON venue in Bangkok. Since yesterday, DEF CON is live, a lot of side events going on here this week. A lot of token engineering people, students from our community, and I'm glad to have you all in this call. Welcome, everyone. And thanks for joining this presentation where we share what we have been working on over the past month, actually, some more details on how we built this NFT-based meritocracy at TE Academy and open sourcing a new repository that allows anyone, any community to build own reputation-based weighted voting. So let's dig in. Let me pull up my slide. All right, so this is all about make reputation count in decision making. And this is a joint project of Token Engineering Academy and 8 Arms, 9 Brains. And that said, I'd like to welcome Octopus here in the call. Maybe you introduce yourself briefly.
Hello, everyone. I'm Octopus. I wear a lot of hats, but today I'm a researcher at 8 Arms, 9 Brains. I've been affiliated with or involved with Token Engineering Academy for almost 4 full years and really benefited from working on the educational materials as both an instructor and a learner. So I'm really excited to talk about some of the work we've done today and how it can benefit communities.
Yeah, and I must say, most of our students know Octopus. He has been course author of TE Fundamentals, Module 3 and 4, and active in the live tracks in the study season and many more of the activities we've been running in the past 4 years. Okay, today we talk about reputation-based weighted voting. And the core idea behind it is that we'd like to make a voter's track record count in decision making, as opposed to, for example, one token, one vote, where you can accumulate voting power due to tokens that you have bought or that are delegated to you. You can, in this case, with reputation-based weighted voting, you accumulate proofs of expertise and achievements as a signal to define the voting weight and decision-making power. And this, of course, is relevant in the voting cases where, for example, we'd like to make expertise count, where we take decisions on a certain subject, where we need domain experts and their perspective to make good decisions. And we applied reputation-based weighted voting in our own community at TE Academy. So in our channels, we have a community of 50K monthly social media reach. We have 20K community followers. We have 6K token engineering read subscribers and 5K token engineering students. So we already have an ecosystem where we have certain degrees of engagement and for sure certain degrees of knowledge in token engineering, which is via people's backgrounds and what they've achieved at TE Academy. And we can track their all community members' achievements in our community via the NFT systems that we've built. So this is a screenshot of OpenSea, the overview of all Token Engineering Academy NFTs that exist. We have today in total 39 different NFTs, and we have minted 1,692 NFTs. And having these NFTs in the system, we have already a pretty sophisticated system overview and proof of the knowledge in our community. And this knowledge is based on the courses, so the TE Fundamentals courses, the various models, and what we cover in these modules. So the introduction, module 2, the discovery phase, the stakeholder exploration, module 3, turning the mechanisms we defined in human language to math to algorithms, module 4, how to build a model and run simulations, and module 5, token-based governance. So these are different focus areas in token engineering, and students are able to take an exam. In case they pass an exam successfully, they can mint an NFT to prove that they have successfully completed such a module. And on the other side, so to say, we have teachers, we have lecturers, like in the study season, live tracks. We had in total 8 live tracks covering different token engineering advanced knowledge, like the token design thinking framework by Sherman Foshengier, Trent McConaughey, with his engineering perspective on data flywheels, DeFi's concentrated liquidity from scratch description by Mark Richardson, and many more. We actually, Octopus and I, ran a live track about reputation-based weighted voting as well, and we had 4 fellowship candidates that brought their past work as candidates for the fellowship grant. So again, we have various contributions here on the knowledge sharing side from experts in token engineering, and they also got a proof of their contribution to the network in sharing their knowledge. So this is a different kind of achievement. And via these different NFTs, we can represent different levels of expertise. Like on the left, the course authors NFTs for creating the TE fundamentals curriculum, or for speakers at the token engineering track at EthCC 2024. They also shared their knowledge and they have expertise in the token engineering sector. Study group hosts. This is again a different kind of expertise, a different kind of contribution to the network. These are local community ambassadors running study groups, supporting others in learning token engineering, or the team who hosted and organized the Token Engineering Barcamp in 2023. So different types of achievements, different types and levels of knowledge in token engineering. And since this is still, even though we already have 1,600, more than 1,600 NFTs minted, we have a certain current distribution in our network when we look at 3 core target groups in the token engineering community: experts, graduates, and students. So once we look at these different NFTs and classify them into these 3 categories, we have experts like the course authors or lecturers. We have graduates, those who have already passed all 5 TE fundamentals modules, and we have students, those who enrolled, who maybe have 1 or 2 TE fundamentals modules completed. And if we look at the distribution, we can clearly see, so the bright green is students, the grass green is graduates, and the blue one is for experts. And today, the experts are actually the smallest group in the community, and the students are the largest group, which is natural in an early stage of the field. However, we wanted to prepare and get ready for a fellowship voting. So we decided in July, we selected the best, one of the 4 fellowship candidates to receive a fellowship prize. And the criteria was, what contribution is most valuable to the token engineering sector? And here, of course, we wanted to have a good representation of expert knowledge and also of graduate knowledge. And once we would weight all the NFTs equivalently, then the beginners would have the most decision-making power. Instead, for the fellowship winner decision, we wanted to have a more balanced decision-making between these 3 stakeholder groups. And our target was to weight them equally so that experts, graduates, and students have equal voting power in this decision, who should receive the fellowship prize. And based on this core idea, we started exploring weighting these NFTs and give this reputation represented by NFTs a certain balanced weight. And generally, if you look at vote weighting, we should first be clear about the steps and components any voting system consists of. So we have at the top voting wallets. I call them voting wallets because in any token system, we have representations of individuals which are wallets. So we don't actually know who's behind a wallet. In theory, this could be an organization, it can be an individual, it can even be a bot. In the case of TE Academy's NFTs, it's students who registered an account at TE Academy. So we have a link between a wallet and a user account. And since the NFTs are not transferable, we can be sure that the wallet that holds these NFTs haven't received it via a trade or borrowed an NFT from somebody else. This is the wallet that is assigned to a student account and can receive an NFT only via passing an exam. Okay, so we have voting wallets that represent students and individuals in our community, so also experts, and they acquired NFTs. Now, second, we have a weighting mechanism that is linked to a ballot. So what decision we'd like to make. In our case, these were 4 candidates for the fellowship prize and 1 candidate to be selected as the winner. And this is referring to the voting rule that we applied. So we need a rule to aggregate the votes. And in our case, this was a percentage assigned of my total voting power to the candidates. And then finally, to compute a voting outcome. So these are the components. Yeah, again, here, just for your overview, TE Academy NFTs, a weighting mechanism, the ballot voting options for the decision to make. In our case, the fellowship prize winner. We had single winner plurality as a voting rule. There could be others, and a voting outcome, a winner. And what we'd like to discuss now is the weighting mechanism. So let's dig in how we weighted the NFTs to compute a voting outcome. And here I hand over to Octopus, because we not only created a mechanism for TE Academy's purpose, instead we are publishing now and presenting an open source repository that is publicly available. And Octopus will walk us through the repository. Let's see how everybody, every community can weight proof to make achievements count in a voting. Octopus.
Thank you so much, Angela. That was such clear and insightful context to set the stage for the actual mechanical work. If you would go to the next slide, please. So we do have a GitHub repository that has tools similar to the ones that were used in the study season. And the purpose of, and we'll go over that code base in depth in a bit. Before we do, I want to give a bit about the context of the problem and what the purpose of the repo is, why it is necessary, and what the design philosophy behind some of the decisions and mechanisms are. So if you go to the next slide, please. And thank you so much for the... So when we looked at the problem, we ended up on a mechanism called dynamic network weight scaling. But to actually solve the problem, we had to think very carefully about what the end result should look like. And we had to ask lots of questions like, what are the requirements for what would we find acceptable? What are the necessary conditions to meet? And what are unacceptable outcomes? And this is not obvious, but for instance, should the person who gets, or the person or the choice that gets the most votes win? That may feel like yes, but there are counterbalances where that may result in other scenarios that are less desirable being possible. And so, as an important part of the design process, we did this requirements engineering, where we're looking at these questions and what would we be willing to accept and what would we not be willing to accept. And that's often the most difficult part, because in this type of work, it's easy for things to become ideological, to think about good and fair, and it's harder to think about if 1,000 voters show up and 10 of them are extremely knowledgeable, is it enough that they decide? But that's the type of ultimate value judgment that the decision makers are having to make in this type of problem. If you go to the next slide, I kind of hit this as a high level summary to think about: what do you want? And what do you need? What do you not want? And then next slide, please. And then how will you know that you have it? And how will you know that you have it, or that you could have it, is going to drive a lot of the simulation work when we get to the place where we're actually looking at different scenarios to see if they produce outcomes that we find reasonable. Next slide, please. As an example of the very, very hard trade-offs that are involved when looking at voting design, there are two very desirable criteria that are in tension. One is what's called the Condorcet criterion. So if you can imagine a ballot with multiple options, but then you went through and only considered 2 options at a time. So if we had candidates A, B, C, and D, we might look at the votes that each candidate received, but then we might consider just candidate A versus candidate B, candidate A versus candidate C, etc. Well, if candidate A would win each of the one-on-one elections against the other candidates, we would expect that they should win the overall contest. And that's called the Condorcet criterion. It's a very intuitive thing that you would want out of a voting mechanism. On the other hand, there's a contrasting criterion called monotonicity, which basically means that if you vote for something, you should not be able to reduce the likelihood that it happens. In other words, there should never be a case where you vote for something and it would have won if you hadn't voted, but it loses now that you do vote. Unfortunately, these two conditions are actually in tension. If you have at least 4 options, you cannot have both. And so right away, we have one of these hard decisions of which one do we value more, or are there certain situations where we would be willing to accept the trade-off of losing one for the other? If you would go to the next slide, please. So our overall goal here is to take the hard math and the hard code that give precise quantifiable results and make it possible to run fast, intuitive experiments and gain insight about what could happen in the different scenarios that we could imagine. The goal here is not to do perfect mathematical optimization that finds the right answer the first time, because that's not even possible in these types of problems. There is no right answer. Rather, the way that we're setting this up is so that you can go quickly through possible designs and get a feel for the design space. And so, like Angela said, each user will have credentials that they're already bringing in. One of the things that's possible with the dynamic network weight scaling is to create new credentials that are based on information from the old ones. So for instance, in the TE Academy study season scenario, there was a graduate credential or NFT that was created for those who had achieved all 5 TE fundamentals NFTs. Then the credentials are placed into groups. And the designer gives these credentials initial weights that are just an intuitive sense of how important or how meaningful each one should be in relation to the other. Then there's going to be the choice of an actual weighting mechanism. We have 2 different ways you can approach dynamic network weight scaling. Once you've chosen the mechanism, then it can calculate and it reweights the credentials so that the total weight constraints on the different groups are satisfied. After the new weights are calculated from the initial information and the chosen constraints, at that point, you look and see how viable, how feasible, how acceptable are the results that we got from the mechanism. It may be that your intuitive idea was far too, enabled far too high a risk of dictatorship. Or maybe it's far too easy to capture with a Sybil. And you can see that through the simulations. And the nice thing is, it will only take a few minutes to do this so that you can go back and try something different if you find the design is unacceptable. Complex systems are best understood through repeatedly interacting with them and seeing what emerges. And this tool is intended for that. So if you find that the outcomes are acceptable, great, you have a feasible design. If not, just go back and try again. And it shouldn't be hard. It should be fast and intuitive for the user. If we could go to the next slide. So I'd like to show what this looks like in the actual code base and talk about some of the, and if I could do screen sharing here, I have this on my local machine. So there's a lot of technical things that went into this of, for instance, creating custom types in Python to enable the data processing. I'm not going to go deep into that in this presentation, but if you're interested in it, you can find that in the reweighting types.py file in mechanisms. I know some of you may be very interested in the more technical aspects of how the engineering actually worked. And so if you are and you want to see the practices that we used here, that's in reweighting types.py. Then there's a lot of code imports. But one of the things that I think is cool that this code base enables is you can create a data file simply in a CSV. And you could either do this as an actual CSV file that you've created in the TE Academy study season. This was created through downloading from a GraphQL subgraph to get the data. And you can see what it looks like as a data frame here. I'm working with a toy data set, not the actual TE Academy study season data set, because I think it's simpler. So here we're just going to have the NFTs are color coded. We have red, blue, yellow, and we have 2 of each. And the scenario we're imagining is that red represents a lot of knowledge and is important, kind of like the expert class that we saw with the TE Academy study season example. Then if someone has all the blues and all the yellows, that's also a lot of knowledge. Blues and yellows are not as valuable as red, but if you've accumulated all of them, you probably have a very holistic picture of the space. So what we want to do now is create a new green credential for people who have all of the blues and yellows. And this is an example of creating a new NFT or a new credential. It may not actually be minted as an NFT, but it's something the system can process based on available information. And then finally, we'll have an other group that consists of everything else, blue and yellow, but not enough to qualify for green. So there's some coding here that creates the green voter and makes sure that is working correctly. And then we're going to create our group rules. So we want to view this not as weighting individual voters, but as weighting total groups or blocks of the credentials. So we call that C weight. And here we're going to have 3 C weights that we need to do the logic of actually finding what should be included when we go to calculate the C weight for each group. The logic here is a little bit, it's not terrible, but if you're less technical, you may or may not enjoy the, I really enjoy the details that went into figuring this out. Others may enjoy it less, so let's not go too deeply into that. Just to say that it's feasible to create any group selection rule that you want. And then this is where the fun begins. A human can set the initial credential weights. So here I have these initial weights set to reflect the fact that reds are very valuable. And I have red 1 at 5 and red 2 at 10. And then blues and yellows are less valuable. And proportionally, maybe blue 2 is more valuable than blue 1 for some reason, harder to get or scarcer. And then these are all of the individual credentials and the initial weights. As the mechanism proceeds, it will work with these relative values. So in the end, it should be the case that whatever the reweighting occurs, red 2 is still twice as weighted as red 1. This is the starting point. And if it turns out these doesn't give the results we like, we can go back and easily set new values. Then we create a reweighting mechanism object. What I would envision here for use cases is that probably most of this is already filled in, and whoever is playing with it only comes and changes these numbers and then reruns the notebook, sees what the results are, and then changes the numbers again if they don't like the final results. So here are some more technical things about creating group masks to filter through the data frames, which will be very exciting for the math code heavy people. I'm happy to go over it if there is interest in that. But mainly I want to show what the mechanisms do rather than how they work. So now like we said, there are 2 different approaches to reweighting this. First is proportional. With proportional, we're saying what percentage of the final voting weight these groups of credentials should account for in total. For instance, I could create that red should be 50% of the total final voting power, that green should represent 35%, and that the other should represent 15%. In the study season itself, these were all set to be equal, I believe, each at 33.333%. You could set these however you wish. Then you actually create the mechanism, and it calculates how much the final weight should be to match that proportion. And after all the work is done, you get new weights. So you can see that the weight of the red credential and the red 1 and red 2 credentials had to increase. The weight of the green credential had to increase a little bit, and that the blues and yellows stayed the same. Now, it should be the case that with these weights for the individual credentials, that the group C weights are as requested, and these are not the proportions, but these are the raw weights, and when you divide by the total, they give the proportions that we looked for of 50%, 35%, and 15%. Now we can kind of look at how that impacted individual voters. So what we've done so far is recalculated the weights of the credentials, but that will automatically change the voting power of individual voters who have those credentials. So we can go through and see a specific voter, how their weight changed, a specific group, how much voting power they have now, And we can just go through and look at the overall population. There's going to be more analytics we can do on this in a moment, but all of the analytics will work off of this data that comes from applying this reweighting mechanism to make the weights fit the proportion that the designer had in mind. The other type of constraint that can be used is an ordered weighting mechanism. And here, instead of specifying exact percentages, you specify the relationships between the groups, saying something like red should be at least as much as green, and green should be at least as much as other. So that if the red group already has more power than the others or more voting weight than the others, we don't need to reweight it. And so you can end up with the two different mechanisms producing the same results, but in certain situations, it's also going to be the case that they'll produce different results. And so this gives a different design option that you can use in terms of thinking about what your community values the most. Do you just want it to be the case that the most knowledgeable block has the most power and that's acceptable? Or do you want it to be that you're actually fine-tuning numerical values? So in an ordered weighting mechanism, it's just about specifying the relationships of what should be greater than what. And it runs through similar type calculations to produce the final results of reweighting. Finally, once the weights have been reset, now you want to look and see if they match, if you find the results to be acceptable, if they match your intuition about how you want things to look. So there are several tools that can be used for this. One is in the metrics directory, the metrics module. There are tools for calculating specific things. Visualization module. There are tools for visualizing. So for instance, I went back and looked at the proportional, the weights that were calculated through the proportional reweighting mechanism. And you can compare how the individual voters had their votes changed in a side-to-side bar plot here. So you can see that the first and second voters both had their relative voting weights increased, and just gives a visual, intuitive sense of whether or not anyone was increased by too much or too little. And you could, of course, go back on this data and make more precise calculations if you wanted to. The other thing that's helpful is to have metrics. So in a moment, I'm going to talk a bit more about the types of metrics that are useful for this problem, and also the glaring need for more and better metrics. If this were like if I'm inviting people to think about research problems, valuable metrics to use for this type of problem is something that it seems to me there's a lot of open room to think about. It's important to emphasize here that the actual results you get don't just depend on the voter weights. They also depend on the voting rule, and I'll change this terminology to match what we're using. The voting rule of how the votes are going to be counted after they're cast, or how the voting weights and the ballots are going to be processed. One of the things in the literature is most of the research about vote weighting assumes that you're just adding the votes up. And so it doesn't account for something like quadratic voting or the mean rule or something like that. So here I'm just working with straightforward add whatever the voters' ballots were up and see what happens. And in order to determine whether or not we get acceptable results, there are a number of numbers, a number of metrics or quantities that we could use to look at different possibilities. One is the Nakamoto coefficient. This is a way for assessing decentralization in voting systems, particularly one token, one vote systems. If your Nakamoto coefficient is low, it means that there is a small group of voters who can control the outcome if they all select the same result. If the Nakamoto coefficient is 1, that means you essentially have a dictatorship where it doesn't matter who else shows up, this one person will ultimately be making the decision. So probably we don't want a Nakamoto coefficient that is too low. On the other hand, if our Nakamoto coefficient is too high, for this problem, we're balancing decentralization against credibility. And it's likely that the credibility is held by a smaller number of experts and deeper community members. So what the Nakamoto coefficient, what the right Nakamoto coefficient is, no one can say, but you can certainly get a sense of what it means. And when you're starting to tend toward things that feel like they're a bit too much in either direction. So we only had a small number of voters. We had a Nakamoto coefficient of the final weights being 2. However, that's not the only thing that we could look at, because that assumes that all of the voters turn out to make the decision. And that's not realistic. So what we would want to look at is scenarios for who might actually show up, what combinations of voters might actually show up, and who has like an effective Nakamoto coefficient for that particular sample of voters that turn out to cast a vote and make the decision. And here we can do sampling, where we take, in this instance, we're doing 10 samples, where between 25 and 75% of the population show up to make the decision. And we can run these random samples and see what the Nakamoto coefficient would be for these random samples that might show up, and visualize what that looks like. Now, because this is a toy example, we only did 10. We're just getting either 1 or 2. It might be helpful to remember that we didn't have that many voters to start with. So what we would get in a more realistic scenario is a larger distribution that shows the likelihood of a larger number of possibilities. And finally, we could do a lot more here. In a moment, we'll talk about other metrics that are useful in other ways to think about how voting power is concentrated. But the purpose here is just to give an overview of potential use cases and proof of concept. Very, very general tools that have been built around recalculating voting weights with specific design parameters in mind. Does that make sense?
Yeah, I wonder if we can stop for a moment and take a look if we have any questions. So feel free to switch on your mic or drop a question to the chat. This was already a lot, and we'll share some additional links in case you want to go over all the mechanisms, and of course also the GitHub repository. So, but in case you want to ask any questions, feel free to do so. All good?
And let me say, we will certainly be welcoming people who want to add. If people have ideas for features or other things, I'd be happy to have help with the technical aspects of things.
Right. So this repository is open source. Feel free to reach out and come up with new ideas, contributions. All right. Good.
Cool.
I think we are ready to continue.
And I'll take about 5 more minutes if that works, and then back to you. Okay, great. Could you share the slides again if you're able? Thank you. Cool. So we just did the code demonstration, and one of the things that the code demonstration pointed to is the need for effective metrics for the simulations. Like we talked about the Nakamoto coefficient already, what that measures, and why it might be bad to have too low a number, but it also might be bad to have too high a number. So thinking about an acceptable range. If you would go to the next slide, please. And I created one that I think is fun called the Swifty number. I was surprised in doing research to find that there aren't that many established metrics for how to calculate Sybil resistance. So like we see in mechanisms like quadratic funding, it can be bad if it's too easy for new people to show up, especially because you can't always tell if new voting wallets are bots, or maybe there's a pop star who suddenly directs their followers to attain interest. The idea behind the Swifty number was that what if Taylor Swift, the famous pop star, told all of her fans to go vote for one of the candidates in your vote? Well, they would show up and get the cheapest possible credential they could, but there would be a lot of them. And in some sense, you don't want that type of social hijacking to occur because they're not highly invested or knowledgeable community members. So the Swifty number, which we came up with, asks the question, how many of these minimally qualified voters would it take to show up and change the results of the vote? If you have a very small number, that's not great. That means that anyone can show up, and it's easy to redirect the will of the established community. But on the other hand, you can't really tell when a new account shows up what their intentions are. And so if it's absolutely impossible for newcomers to affect the vote, that may or may not be desirable either. I remember, one of the things about this work is it arose out of a learning experience that we had together, and there was a great mechanism called Group Hug designed by one of the students named Joanne, which could not be affected by any type of Sybil resistance because of the way that votes were partitioned before they were counted. And that was really cool because it gave a level of security in terms of guaranteeing that the final outcome couldn't be hijacked. If we could go to the next slide, please. Okay, we just did a code demonstration, so I might have had that twice. And now, Angela, I hand back to you. Thanks so much for letting me be heard.
Yeah, thanks for walking us through this repository. And now let's take a look at how this voting and reweighting the votes in the TE Academy ecosystem turned out when we made this decision on the fellowship prize winner. So again, we had these different levels of expertise ranging from course authors to speakers at events to TE fundamentals, students, study group hosts to team members who helped us organizing the barcamp. Very different levels of expertise. And we had this goal in mind, this target, that we have 3 key stakeholder groups: the students, the graduates, and the experts. And just like Octopus presented us, we defined a C weight. And in our case, we wanted to be the C weight, so the total weight of all existing NFTs per stakeholder group, to be the same. And this is what we see on the right, and on this right diagram, C weight that was equal for all 3 stakeholder groups. Now, here on this chart, we see how we reweighted the NFTs in our ecosystem. So first, the dark blue weights are this initial definition of the weight. So you might remember in the code, this initial setting predetermining the weights for different NFTs. And this is what we did in dark blue. So we already knew there are some NFTs who represent not let's say a very deep understanding of token engineering, and other NFTs that represent expert knowledge in token engineering. And this is this predefined weight. And then after the reweighting, according to this target that every stakeholder group should be in, the accumulated weight in the stakeholder group should be equal, we had the bright blue weighting. And as you can see, for some of the NFTs, the shift was huge. And for others, the weight remained the exact same. And this diagram on the right, again, shows this from a different perspective. So we have the NFT supply, which is the dark blue line, and the weight by token ID. And here we can clearly see that NFTs in low supply, very scarce NFTs, typically expert NFTs, have then ultimately to achieve this balance, have a higher token weight, and those who are in high supply, so we have some of the TE fundamentals modules, have a lower token weight to then overall land at these equal weights for stakeholder groups. Now, how has this affected the voting outcome? Again, the decision to be made in our ecosystem was who should be the fellowship prize winner. We had 4 candidates, and the question who deserves the support of receiving a grant, the prize was 10K, and we wanted the community to decide. And this is the result if we look at these stakeholder groups after the re-weighting. So we have the voting outcome and now can analyze the NFTs and the wallets holding a certain set of NFTs and can now understand, okay, what was the students' opinions on 4 candidates? What was the experts' opinions? And what was the graduates' opinion? And using these weights, we can see that experts obviously had a different opinion on who should receive the prize. And grades and students were very much aligned. And ultimately, this led to candidate D to be the prize winner due to the weighting mechanism, which would have been different when we only count the NFTs held in the ecosystem. Okay, let's see. Yeah, I think we can sum it up. So the steps to design reputation-based weighted voting is think about what's the decision to be made, what's the question, what achievements should count and how they can be proven, what proofs should be integrated. In our case, we used NFTs. There can be other attestations, tokens. In theory, we could even use Web2 credentials or a combination. How to weight these proofs, how to balance a weight, how we can even combine, as we have seen it in the GitHub repository, we can give certain combinations of proofs, a dedicated weight, and then we start defining weights. We can start with an initial definition, like we did, and then start reweighting and verify these weights parameters, adding metrics to observe the outcome, like the Nakamoto coefficient or the Swifty number. And once we feel that we landed at a proper parameter setting that is also safe so that nobody can easily take over the voting, and we have achieved the core idea and the objective in the reweighting, we can roll out the voting with new weights that are assigned to proofs and roll out a voting where achievements and a track record counts in the decision making. That's it. You can contact us and find us at Tok Engineering on Twitter and Farcaster or 8 Arms 9 Brains. Always happy. Just message us if you're planning something similar. If you have questions on the repository, if if you have new ideas on reweighting mechanism. And I think we have some minutes left just in case we have questions.
I would
Also,
have a...
Octopus. Oh,
Sorry.
Arena, just a second. Octopus,
Yes,
can you
yes.
drop the link to the repository to the chat as well to make it available?
Yes, I will also say there are always new branches rolling out. So what you look at today will probably change before next week. But yeah, I'll be happy to drop the link.
Cool, thanks. Arena.
I
Hello.
wanted to ask if you, hello. First, I mean, thank you for the presentation. It was really interesting. I wanted to ask if you can have a, if you have a comparison to earlier voting, if the motivation of the actors somehow changed when they knew that they had, like that their vote had a lower or higher weight.
Actually, this is pretty interesting to see, because we discussed, so the whole study season, LifeTrack 4, was dedicated to designing this reweighting system from scratch. And we had a group of students that were focusing on the end-to-end design of this mechanism. And one of the big topics was, to what extent should be the final weight visible to the voter? And it turned out that this is a pretty important aspect, or it was for our students, and I'm sure it was for every voter, to see my voting power in comparison to others who maybe have already voted. Because this is like, it gives you an impression on the final impact you yourself have on the voting outcome. Now, one could assume that the moment you find out that you have very little voting power, you are demotivated. And the moment you find out you have very high voting power, this is an additional motivation to go to vote. We didn't collect data on that. I mean, in our case, you only saw it once you were voting already. So we didn't publish it beforehand. So though there was no way to gain insights on your voting power other than voting. And maybe this is the key, right? So direct people to the voting, then they see their voting weight. Of course, sometimes it might be more or less than expected. And this can, in theory, have an effect on the voter motivation. We don't have any clear data. What we definitely can confirm is that voters are interested to know their voting power. And it's definitely an additional motivation to take part in this decision-making, to gain an understanding, where am I in terms of decision-making power, and how does this relate to all other community members' voting power?
Thank you. I think it's really interesting. I mean, it's like, especially also as a social experiment, when we see that the voting might not actually in the current system like work as like for the expert voices as much as would be favorable. Is there any like way how to actually like share like the expert like in discussions like previously voting? Because I mean, maybe like when I joined, sorry, my kids are here, and like when you know, like I join and have like a low voting power, I know that I'm new, I don't know that much. I want to know kind of like who the experts are, and I would maybe want to know kind of like how are they voting, not like in a delegation sense that I would kind of like give them my vote, but I would want to be like, okay, that's those people, they have like the highest voting power in the community. I want to know actually who they are deciding for, and that might be like the candidate or the cause that I might want to have a closer look at. Is there some kind of like apart like from the voting system itself, were you also looking at some kind of like social and communication structure pre-voting, like how to kind of promote this kind of like exchange and like maybe some like sharing of information in before the voting itself?
Yeah, this is also a super important question. Before we dig into that, I just want to give a huge shout out to Vitor Martindal, one of our community members who implemented this whole voting system in Snapshot. We've used Snapshot for the voting, and in the Snapshot, let's say, set of tools, you can find Shutter. And Shutter is a tool that prevents voters to see what all other voters voted during the voting process. And this is a choice every community has to make. Should it be a private voting or should it be an open public voting? And this refers to your question, Irina, because I think it's a very important decision to make. And we also, we discussed what would be the most viable route for us. Now think about it. You can have public voting. In this case, you would see in Snapshot, this is how it's set up by default. And of course, in any other voting tool, you can design it as based on the requirements you have. In Snapshot, you see once a voting is cast, you can see the voting weight of this wallet. And some people have an ENS domain assigned to this wallet, so you could even identify an ID, a Twitter account, or even a person. And then you see this person, this vote, and the weight. And this way you can get exactly the information you're pointing to. Who are the experts? High voting weight. And what was their choice in the voting? And this is a piece of information that might inform the total community. However, I would say in many decisions, the beauty or the actual why do we vote, we'd like to provide the community to signal their preference and aggregate this variety of preferences in one single outcome. And the question is, if you want to come to a consensus via a discussion where it's good that people inform each other about their choice and take a look at what others do and even make recommendations, then it's probably, the question is if voting is then the right tool, because what's the strength of a voting is that you have anonymity, that you avoid groupthink, that you try to land a result where it's not the opinion leaders who are like actually make their choice and all others follow. In a voting, the strength is that you can aggregate very different opinions, if you like, in a private fashion, so that everybody can vote according to true preferences. And that might be, let's say, distorted if you have a public voting. Because, I mean, in crypto land, we have a lot of opinion making, leadership, evangelism, and a public voting. In our case, we decided to use Shutter to have a private voting to make, to allow every community member to vote according to their preferences and not just follow the most, the wallet holding the most voting power. That was our intention. I hope this makes sense.
Yeah, absolutely. I think like it's will be also, I think, in the future a bit difficult to find the balance between that, because there's also like a difference between someone who's like very loud on social media and someone who actually does have the credential and the knowledge of the system.
Right.
Because what I see in DAOs is also that what holds people from voting is actually that they feel like, oh, I don't like have the time to kind of like dive in deep, so then they kind of like vote just like quite random, that they kind of like just, you know, like quickly run through something and they're like, oh, okay, like by gut feeling, this sounds the best. So they cast a vote without actually studying the matter, or they actually don't vote at all because they're like, yeah, I really don't know how to decide on it. So this kind of so I think like generally to have some kind of possibility, like not to make the vote kind of like, oh, they voted like this, so I'm gonna do that too, but more kind of like to be able to have some kind of like, okay, this is actually a person I trust. Me personally, it's not kind of like official delegation, but I like know this person like is usually kind of aligned with me, so I'm gonna like do what they recommend. So it can also kind of like higher up the voting motivation to know kind of like what the expert opinion is, and the expert opinion like in the best case would also vary, that it wouldn't be just kind of like, oh, all the experts are just for this matter, so that they would do that. But yeah, like generally I think like the voter motivation gets like often stuck on this kind of like not enough deep knowledge of the subject matter, and then it's kind of like, oh, then I better not do it at all. But yeah, it's a difficult question altogether, but I really like the weighted vote mechanism. It really makes sense to kind of like push forward the expert opinions.
And I must say there's a lot, I mean, here at DEF CON, I had a lot of conversations on how to solve this problem on voter fatigue, also on this question of expertise in the voting. How can we make sure that we really build on informed decision-making? I think these are really tough nuts to crack. I'm happy to see that a lot of DAOs and researchers are working on these problems. And I'm sure we'll see a lot of very interesting solutions in the upcoming month. And yeah, hopefully reputation-based weighted voting is one of them, or points in a direction. Check out the repository. The room is getting crowded now. Thanks for joining, everyone. Check out the GitHub, follow us on our Twitter accounts, and always feel free to reach out. Thanks for joining the session today, and talk to you soon, everyone. Bye.